So how do we measure EEG? I touched on this a little last time, but in a little more detail today. The key components are you need to have electrodes to put on the scalp, right? And you need to have a human with a brain from which to record. And then the electrodes run into a box, which we call the amplifier. So that basically boosts the signal that's coming off the electrodes and digitizes it. So it turns it from a continuously varying, basically electrical signal voltage to a digital signal that then gets recorded on a computer. And in most setups, you have one computer that's doing the EEG recording and then another computer that's controlling the stimulus presentation. In principle, it's possible to do it all on one computer, but in general, the software is not set up to do that. And so we use two separate computers, and that provides some advantages in that it means that, basically you can control the screen on the stimulus computer, and that's what the subject's seeing. The other screen, you can diddle with the EEG data and so on. So those are the basic things. And then last time I also showed you this figure with the different types of electrodes, from the very sort of classic ones over on the left, these ones in the middle with the little digital preamplifiers on them, and then these ones which have sponges in the net configuration. But at the end of the day, they're all basically bits of metal touching the head in some way with some wire connected that runs to an amplifier that then runs to a computer. Nowadays, I don't have images of it, but there are a few systems that are wireless, either using Bluetooth or Wi-Fi to stream the data, in which case you just have some sort of little heavier pack attached to the person, either on the back of the headset or on their belt, that serves as the sort of data collection amplifier that then streams the data out. I haven't seen a system where there are actually wireless electrodes. So the electrodes would still have wires running to the thing, but at least then you're not tethered to a computer. And then the other thing is there are a lot of different ways of making electrodes and attaching those electrodes to the scalp. So the conventional method is what we would call wet, because the other method's dry. So in the wet method, you have some sort of metal like tin or gold plated or silver plated electrodes, and then some gel or paste to make the connection to the scalp. And this is important because in a wet system, one of the advantages of having this wet stuff like gel or paste is that you don't actually have physical contact between the metal of the electrode and the scalp. And instead you've got this sort of squishy interface between them. And the advantage there is that if the electrode were to actually physically be touching the scalp, any movement would be really magnified and would really affect the strength and the quality of the connection. Whereas if you've got the gel or the paste in there, little movements at least, the electrode will sort of move, but you've got this wet stuff that moves with the electrode, and so the contact doesn't get as messed up. In general, the difference there is that the paste is almost like glue, so it's conductive, but it's really sticky. So if you go to the hospital, if they think you have epilepsy or something, they want to do a clinical EEG, they'll measure your head and stick each electrode on individually with this paste. And that paste will last for, it can last for days. Whereas in a research setting, it's also really messy to get out. In a research setting, we have the stretchy caps that you saw in the previous figures. And we'll put that on. It holds the electrodes in place. The gel we squirt in. The gel is water soluble, so it's a lot easier to clean up after the fact. So that's really the big difference, is how long do you want that on for, and how difficult is it going to be to clean up at the end. The other thing is, as you've read about in the chapter, you want to get low impedance between your electrode and the scalp. And so the gel or the paste helps you achieve that low impedance. It's conductive, and then you'll actually use something like the syringe you're using to squirt it with, or a little wooden stick to kind of massage that into the scalp to really work it into the pores and get a good connection. And that's really critical, because when you have high impedance, you pick up a lot more noise in your recordings than if you have lower impedance. And as I mentioned already, they're resistant to movement. The dry systems, the electrodes are often made out of graphite or carbon. Sometimes they do have a metal coating on them. I've seen ones, they're actually like these little styrofoam, they almost look like spider legs, like these little sort of things. And the idea is they sort of part the hair, and they're in like a cap kind of configuration that you can tighten, and so as you tighten, they sort of push down and spread out to get a really good connection. And that's one of the big issues with the dry ones, is how do you ensure that the electrode isn't constantly sort of popping off and that it's really pushed on. I didn't have a chance to grab any pictures, but usually the dry electrodes, instead of being like a flat disc or something, they look like those spider legs or some sort of spiky, multiple spikes on the electrode, kind of, as I said, get through the hair, and then you need something tight that pushes them against the head. The issue with dry electrodes is that they have high impedance, exactly the reason that we normally use gel or paste. We don't have there, and so you don't get as good quality recording. It's going to be much noisier, it's going to be more sensitive to head movement. And the reason that people have bothered to develop dry electrodes is that there's a lot of interest these days in what they call like consumer grade EEG, or EEG in situations where you might just want to put it on and not take the time to fuss with the gel. How many people have heard of the Muse headset? Nobody? A couple of people. So this is actually a Toronto-based company, Interaxon, who developed this headset that sort of goes across your forehead and clips behind your ears, has built-in headphones, and then it's got an app that teaches you to meditate and basically help you relax. And it's actually recording your EEG from electrodes on the forehead and over here, and looking at particular frequency bands. And when the power in those frequency bands goes up, that's associated with states of relaxation. And so they basically are doing this neurofeedback, where they're measuring these brain states and translating that into sounds. So it's like, sort of an ocean sound effect, sort of soundscape. And if your mind is more relaxed, it's very soothing kind of music. As your mind gets more, as your brain waves get more sort of agitated, you'll get like stormy sounds and this kind of thing. And there are a lot of other interesting applications people would like to develop, at least around this, just being able to provide a headset to somebody, stick it on your head, don't worry about messy gel and so on, and just go with it. So that's really the push towards dry electrodes, but at the same time, the data are always going to be noisier and worse. So in a research setting, there's no real reason to use a dry electrode system. You might as well get the good data and use the wet system. Right. And there's a standardized system for how the electrodes are arranged on your scalp. Not every system uses it. Most of them do. The biggest exception is that net system that I showed you with the sponges. As I mentioned last time, they have a geodesic dome configuration, and so everything's sort of designed around these evenly spaced triangles. The idea of this system, called the International 1010 system, historically the International 1020 system, is that it's based on sort of a standard reference set of measurements that you can make on any head, so that the electrodes are spaced evenly across the head. And this came from the days before EEG was done with caps, and still, as I mentioned, in the clinical setting, they stick the electrodes on individually. And so the idea is that you measure from the bridge of the nose, which is marked NZ there for Nasian. So this is sort of the indentation at the top of your nose before your forehead. So you measure the distance from there across the top of your head to the inion, which is the bony base of your skull. Sort of right, if you feel behind there where the soft part turns into bony skull. So you measure that difference, and at 50%, so halfway between those 2 points, that's the center of the head, what we call CZ. And front to back, and then left to right, you take points that are the same on either side of the head. It's a little arbitrary. I like to say, okay, the tragus is like this little flap here. If you measure from the top of the tragus, that's a pretty easy one to find on just about everybody's ear. Go across the top of the head to the top of the other tragus. If you use the bottom of the tragus, the earlobes, it doesn't really matter as long as you're using the same reference point on both sides, because we assume heads are relatively symmetric and ears are relatively symmetric, and we just want to know half the distance that way. And so that gives us CZ by measuring left to right, front to back. And then all these other ones, it's called 10-10 because it's based on 10% increments. So basically, if you count, there's 10%, 20%, 30%, 40%, 50% of that total distance and moving back. So even if you don't have a cap, you can take these measurements and figure out where each electrode is going to go just by doing measurements and a bit of simple math. And the same here, they're in 10% increments out. So it doesn't really matter how big your head is. You just get those two measurements, front to back, left to right, and you can get all these electrodes placed in the same relative positions on any person's head. Historically, it was a 10-20 system because there were fewer electrodes and they were done in 20% increments rather than 10. Or it was kind of a mix of 10 and 20, hence the 10-20 system. Now everything's done 10-10. There's also a system called 10-5 where there's more electrodes and they're spaced at 5% increments. So it's sort of flexible that way. The other thing I'll point out about this system is there's lots of letters and lots of numbers. Everything actually makes sense once you start to think about it. So C stands for central, F stands for frontal, P stands for parietal, O stands for occipital, T stands for temporal. So they're basically the different lobes of the brain, and then central is the central sulcus. So you can see they sort of go down C, 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 down there until you get to the temporal lobe, and then the T's. And then odd numbers are on the left side of the head, even numbers are on the right side of the head, and Z stands for 0, right? So CZ is 0, so it's at the center, C1, 3, 5, C2, 4, 6, as you go in the other direction. And then like FC is between the F and the C, right? The very front gets a little confusing. FP is for frontal polar, so the very frontal part of the frontal lobes is called the frontal pole. So that makes sense. And AF, I don't really remember what the A stands for, but the AFs are just these ones that are sort of squished in between. I don't think we have the AFs on our cap anyway. All right. There's a question of how many electrodes you really need to use to record EEG. There's certainly a bare minimum, which is 3. We'll talk about that in a few minutes. In principle, more electrodes gives you more data. That's not even a principle, that's a fact. In principle, more is better in the sense that, you know, the brain has lots of stuff going on, and we don't have that many electrodes, so it seems like more electrodes would give us more information. The issue is that, as I've already talked about, the skull is a very poor conductor of electricity, and everything that's going on inside the brain sort of radiates out, mushes together, hits the skull, kind of gets smeared out. And so what you record at the scalp with EEG electrodes is actually pretty low spatial resolution. It's very spread out. If you ever see anything that's very focal at like one electrode or a couple of electrodes in EEG, it's probably not actual brain data, because that's it's physically unrealistic to imagine something that focal being recorded through the skull. It's probably some sort of artifact. So that's one practical limitation, is that there's sort of a fundamental limit on the spatial resolution of what you're measuring, independent of how many electrodes you put on there. Another one is that with most systems, it takes more time the more electrodes you have. And so like with 64 electrodes, which is fairly common to use, that takes 30 to 40 minutes to put on somebody's head. So already that's a lot of time. If you have a 1 hour time slot for your experiment, that's already probably like too much time, or at least it only leaves you 30 to 20 minutes for your actual experiment. So obviously you don't want to go higher, maybe you want to go lower. Another issue is that as the electrodes get closer together, you run into this risk of bridging, which is basically where whatever you're using as conductive material, say the gel, spreads out, and say you've got, I don't know how to do this on my forehead, so you've got 2 electrodes on your forehead close together. As the gel starts oozing out, what's going to happen is eventually it's going to touch, right? So the gel from the 2 electrodes is going to sort of ooze under the scalp or under the cap and make a bridge between those 2 electrodes. And at that point, you're not recording from 2 distinct electrodes. You're recording from the entire surface area that blob of gel is touching on your scalp. So those 2 electrodes aren't giving you independent sources of data. They're giving you the same data. So why did you need 2 electrodes? You could have just had 1, right? So the tighter packed you start putting those electrodes, the more likely you are to have that bridging effect. It's a reason in general to not use too much gel when you're putting it on the electrodes, but it's another reason to limit the number of electrodes that you're actually using. Another one is that during the recording, you're going to monitor all of these electrodes, and sometimes the electrodes sort of shift or start giving you bad data. So the more of them there are, it takes longer to get them set up in the first place, and it's more to have to sort of maintain and keep track of as you're going along. And then it's more data that you have to analyze and interpret, which in principle isn't necessarily a bad thing in these days of big computers and big data and all that. But again, if there are other fundamental limitations that, you know, giving you more electrodes doesn't necessarily give you richer data, then there's not too much value to it. This is a study that was published quite a few years ago now, and actually by researchers, including the guy who founded the company that makes the net. The net system has always pushed high electrode counts, so they make 128 and even 256 electrode configurations. So you have to take this with a bit of a grain of salt because there's some sort of commercial interest here. But what they did is they modeled dipole sources and how those would project to the scalp. And here what you're seeing is the number of electrodes that are on the head. And then here you've got two different configurations in terms of the number of sources. So this has 4 sources, this has 7 sources. And with 4 sources, you can see that basically, so this is 19 over on the right, 32, 64, 128. So you can see that with 19 electrodes, you don't get a very good picture of the 4 source configuration, but once you get up to even 32 electrodes, you're pretty much getting the same information as you are with 128. On the other hand, when you've got 7 distinct sources in the brain, it's not till you get to 64 that you really start capturing that, and then 128 where you really get that fine-grained separation. The catch here, I said there's commercial interest. This looks nothing like anything that you would ever see coming out of a human being's brain, right? It's modeling something that is biologically implausible. So it's not really the best test case for it. But it does show you that you can get some benefit in some cases to going higher. In practice, though, there usually aren't that many distinct things going on at the scalp. And usually in an ERP study, you're not interested in capturing, it's not like fMRI where you're interested in capturing fine-grained spatial patterns. Usually in EEG, you're designing your experiment around a particular component or frequency band, right? So say you want to look at the P1 or the P300 or the N400. And any one of those components, you really only need 16 electrodes to be able to measure that, because you already know where it's going to be biggest on the scalp, you know what the timing is, you design an experiment to elicit it. And with any of these components, there's such a history already published of what this component looks like, where it is, and so on, that you don't need 128 electrodes to capture it. You can get it with relatively few electrodes. So I showed you this last time, but this is showing that, with 3 sources here, bottom left, you can see 3 sources in pretty far apart, so like the 2 temporal lobes and then one sort of more centrally. So those are about as far apart as you can get within the brain, and yet when they're all active at once, you get one basically scalp distribution. So one sort of negative peak and then a positive peak that's not even showing up on the head. And so again, it sort of begs the question of how many electrodes do we really need? Well, we probably need, one in the center here. If you imagine you had 5, so sort of front, middle, back along the midline, left, middle, right, you would be able to capture that fairly accurately, that the peak negativity was at the central electrode, weaker at all the other ones. And as you added more electrodes, you'd just be sort of saying that story with maybe a little more authority or detail, but it would basically look the same. And the reality is, even when people do use like 64 electrodes, they'll often do something like this and chunk the electrodes into groups when they actually get to the data analysis point. And so this is what we call regions of interest, or ROIs, where you select an area and group everything together and just analyze that. If you're familiar with ANOVAs for doing statistical analysis, if you were to use an ANOVA with this, you just sort of model 3 levels front to back and 3 levels left to right as variables, and that would capture the entire scalp distribution there. And you wouldn't get a lot of benefit from modeling whatever we have for 11 levels going left to right, because again, these effects are so widespread across the scalp. In what you'll be doing in this class, we have a 16 electrode montage, and that is absolutely adequate for any experiment you're going to design. All right, so that's sort of the overview of some of the basics of EEG recording, and then the rest will really cover hands-on when you learn actually how to work with the EEG equipment, and as I say, in the lab when we're working with data and so on. So now I want to step back and talk about the sort of physics and mechanics of EEG recording, starting with what is electricity, because ultimately we're measuring electricity coming from the brain. So just a few terms to throw out there. Electricity is the movement of charged particles. Typically electrons is what's going on as electrons are moving through some sort of conductor. When we talk about voltage, what we're talking about is the potential for current to flow from one location to another. And this is really critical, and we contrast that with current, which is the actual flow. I'll get to an analogy in a minute, but current is when there's actually something going through, so you can be electrified by electrical current. You can't be electrified by electrical potential. Another way of thinking of it is when you buy batteries at the store, right? Those batteries, like an AA battery or something, is 1.5 volts, and that's its potential. And it's 1.5 volts even if it's in the box and it's not connected to anything. Whereas the current is only flowing when you actually put that in your flashlight or whatever device, turn it on, and you're using power from that battery. That's when the current flow is happening. And then finally, resistance is the prevention of current flow. So things like copper, very good conductors, have a very low resistance. Things like wood or skull have very high resistance, so they're poor conductors of electricity. In EEG, we don't talk about resistance, but instead we talk about impedance. And this is sort of a subtle difference. It's really that resistance is relevant when you're talking about alternating currents, and impedance is relevant when you're talking about direct currents. And we're always dealing with direct current in the brain kind of situation. Resistance is more relevant when you're plugged into a wall because that's using alternating current, but that's a little bit beside the point. Really, you can think of resistance and impedance as equivalent for sort of conceptual purposes and the purposes of this class, but we always say impedance. All right. So again, electricity is the movement of charged particles, and these experience force in an electromagnetic field. We'll come back to the relevance of that. And again, this notion of a dipole, so you've got positive and negative polarity. The water metaphor, I think, is really the easiest way to understand the concepts around electricity. And so the potential, as shown here, is you imagine you've got some sort of vat of water. The potential is sort of, you can think of that, say I'm holding, well, I've got a water bottle here, right? To be safe, I'll put the cap on. So we currently have a potential of 24 ounces of mess on the floor, right? We have a potential mess on the floor, but we have no actual mess on the floor because nothing's flowing at the moment. So that's the concept of potential, is it's how much difference is there in water between one location, in this case my bottle, and another location, in this case the floor. The current is, if I were to actually, and I'm not going to pour water on the floor, that'd be fun, but I'm not going to. But if I start pouring the water, I'll pour some into my mouth. Now the current is the actual flow of water from one location to the other. So again, with the battery always has the potential, but it's not until you turn this switch on and have that battery within an electrical circuit that you actually have current flow going through. And then resistance in the water analogy is really how big is your pipe, right? So less resistance, more current flow, more resistance, less water can get through, so there's more resistance and less current can flow as a result. And then these things are actually related mathematically. So if you haven't remembered from before, this is current, this is resistance, and that's potential. So these things, current, resistance, and potential, are all related to each other. That's not on the test, but worth knowing. And you can see the real take-home there is that what we record from our EEG electrodes is a function of how much current is in the brain and the impedance. So how much is going on in the brain and how much resistance do we have to that current actually passing from the brain and ultimately from the scalp into that electrode and into our recording system. Yeah, it's just yet another illustration of concepts. So in the brain, when we're recording EEG, what we're recording are electrical potentials, and that's critical. The current flow is generating something, but it's really potential that we're measuring and not current flow. So if we go back to what I was talking about last time in terms of how EEG is, where does it come from in the brain. We talked about these open field configurations where you've got neurons that are all aligned basically parallel, and you've got coherent synchronized input coming into those neurons so that their postsynaptic potentials on the receiving end, which in this case is the top on the left here, everything is sort of coherent and synchronized. So in this case, we've got more positive charge up there. As a result, we've got more negative down there. And I sort of talked about this last time, but really drive it home this time. It's really a relative difference, that if these neurons had sort of the same electrical potential, so that sort of the same balance of positive ions and negative ions inside and outside the cell membranes across the entire neuron, once you start getting this input from other neurons, if that drives the cell body end of this open field to be more positive, then the other end is going to become more negative, just in relative terms, right? So the other side didn't really change, it's just now this is more positive, and so now we have this electrical potential difference between either side of our open field. And then this is just sort of contextualizing that on the right in terms of inside the brain. And when we get to the recording, we're sticking electrodes on the head, and what we're measuring, as sort of a preview for the next section, is the potential difference between different electrodes. So even though, as I showed you last time, when you record the data, you get a little tracing from each electrode on the scalp, that's not actually just that electrode. It's the electrical potential difference between that electrode and some other electrode on the scalp, which we call the reference electrode. So we've got reference and ground here. So again, electrical potential is always measured relative to something else. In my example with the water, it was the difference in the amount of water in my hand versus on the floor. Now, if I was like in scuba gear and I was underwater and I had a bottle of water, there's really no electrical potential difference, water hydro potential difference between my bottle and the environment around me, right? Because if I open that bottle, there's water all around. It's really that there has to be that difference. So the same here, there has to be some difference in the relative electrical charge in two locations. So in EEG, the question is, what is that relative to kind of thing, right? When we're talking about, well, we've got this one electrode on the scalp. And ultimately, we measure electrical potential relative to ground, which is the Earth. So the Earth inherently has zero electrical charge. And in an electrical system, we talk about ground as something where the electricity, like any sort of residual or excess electricity, can flow. And so having a ground in like your three-prong plug is a safety feature, so that if there's some issue with the current flowing through the system, it gets shunted into the ground and into the Earth, which can absorb it, rather than you touching the washing machine or something and getting it flowing into you. But what we don't want to do in an EEG system is connect our subject directly to the ground, because that means that the current could pass from them into the ground. It becomes a safety issue. So there's sort of two parts of ground: is a place for electricity to flow, but also as a reference point to define absolute zero in terms of electrical potential. But because we can't include the earth ground in our system of EEG recording because it's a risk of electrocution to the subject, we need to have some other kind of ground. So this is what we don't do. The ground here is the G. In principle, we could do that, and that's sort of the ultimate reference, right? Is what's the electrical potential at this electrode location on the scalp relative to this absolute zero kind of reference that we have. So as I said, one issue is the safety issue, but there's actually another issue, which is that the body overall is a very good conductor of electricity. And that's why you don't want to stick your finger in a socket or something like that, because the current will flow through your body, through your heart, disrupt your heart's electrical activity, and you'll die. So your body's a good conductor. And what that means in this context is that if you stick one electrode on the head and record it relative to this sort of earth ground, what you're measuring is the electrical potential of the entire body, not just of the brain or one location on the brain, because everything is sort of contained within your body. So we can't do that. So because we're going to get the brain activity around that electrode, all the other brain activity, all the other activity in the body. So we need to control things a little better. And so that's where this notion of common mode rejection comes in, is that we're still going and, this is for convenience for explaining for now, ground is still the earth ground, but the way that we can isolate the electrical potential at this electrode relative to the rest of the body is by sticking a second electrode somewhere else on the body and using that as what we call a reference. And so that one is basically each of these is going to measure the electrical potential of the entire body. But we can do a subtraction between the two and say what's going on, which will subtract what's common of those two. And then what we get left with is the electrical potential difference between A and R here. Okay? So again, each one of those electrodes relative to the ground measures everything. But because they're at slightly different locations on the head, they're going to pick up slightly different signals, mostly driven by the brain activity that's close to those electrodes. And so now we can actually isolate the brain activity from all the other electrical activity in the body, coming from your heart, from your muscles, from whatever your body's picking up from the environment. And so that's because everything's measured relative to ground, so active minus ground, and then reference minus ground, take the difference between those. So that's really the key principle here in what we call common mode rejection. The common mode being just all the electrical potential in the body together. And that's essentially how all EEG amplifiers work. The real sort of subtle difference is that we don't want to electrocute our subjects. Yep?
So if we have no here, why the minimum number is 3 electrodes?
I'm coming to that. Good question. It's like I paid her to ask that question. Because we don't want to electrocute our subjects. And so we need a ground that's outside of the, that's not the right way to say it, a ground that's inside the sort of recording system that we have. So to define what's zero, what's no electrical potential, a special circuit is set up inside your EEG amplifier, and it basically uses that as the ground rather than connecting to the earth. And it means that we don't know the absolute electrical potential of your brain relative to the earth, but it turns out that doesn't actually matter for recording EEG. What we care about is the relative electrical potential between these two electrodes, and we just need that other one as a reference to be able to measure an electrical potential at all. The only issue is that the amplifier itself will have electrical noise, and so we need to cancel that out, and that's where this third electrode comes in, which is the ground electrode. And so now we have a ground electrode put somewhere else. It's not always on the forehead. The location of the ground is actually relatively arbitrary. But now everything's connected to the scalp, and we run this one into a separate circuit in the amplifier that is the ground circuit. And so it serves as a reference. So again, it helps subtract out all of the sort of noisy background stuff, the electrical potential that's present throughout the body, and isolate the difference between our active and our reference electrodes. All right. Does that make sense? Basically. It's probably one of the harder concepts to grasp in this class. And hopefully I'm doing, between me talking and me writing, a reasonably good job. It took me a long time. It wasn't until I was really teaching this class that I felt like I actually understood these concepts. So A, you can do EEG without ever really understanding these concepts. And B, don't be too stressed if everything isn't crystal clear, but go back and read again. In practice, what this means at the end of the day is to get good data, you need, to do EEG, you need a minimum of 3 electrodes. But critically, coming back to this concept of impedance, whenever we put electrodes on the scalp, we want to minimize the impedance between the electrode and the scalp. And we want to do that at every electrode. But it's especially important to minimize the impedance at the reference and the ground, because every active electrode, so basically we have one reference, one ground, and then all of our 16, 32, 128, whatever other electrodes are the active electrodes. And the signal that we record at every one of those active electrodes is only as good as the impedance at the ground and at the reference and the impedance at the ground. And so getting the impedance really good on those is important. And that can actually be tricky because in most systems, when you check the impedance, you get this visual display, and it doesn't actually show you the reference or the ground impedances. Because what it's doing is it's actually, to measure impedance, it's passing a current in through the ground electrode. Very weak current, you won't feel it, not harmful, and measuring that at every other electrode. And so as the impedance goes down, the strength of that current flow is better, and you get a better impedance recording. And so you have to make sure that that ground electrode, you just sort of work it, make sure the gel's really worked in and get a good connection. And that, in my lab, I've found is a very common problem, is people get everything on, they think the impedance looks good as per the measurements they get off the computer, and their data still look kind of gross. And I'll come in and just sort of poke at the ground electrode or the reference electrode, and often everything will get super clean really quickly. So it makes a huge difference. So that's really the big take-home message. But then understanding why that matters and keeping that in the back of your mind when you're doing it is helpful, that it's because these things are critical, that every electrode is measured relative to the reference and to the ground. All right. So then the question becomes, what to use as a reference? Here you can see somebody who's got an electrode on his nose, and that is historically a not uncommon reference location. And Pinocchio would be the ideal, well, in some ways. Pinocchio as real boy would be the ideal. Obviously, as a wooden boy, he's not very electrically conductive. We probably wouldn't get good EEG anyway. But the idea of putting it on the nose is sort of, this is the magnification of that, is that the nose is kind of far away from the brain. And so we want to put our reference electrode far away from the brain because we want to measure the activity at each active electrode and subtract out all the stuff on the body that's non-brain signal. This is a set of common ones. So the nose, the nasium, so the bridge of the nose, the vertex sometimes, top of the head, middle frontal is what's set up in the system we're using for this class, or the mastoids, which if you feel behind your ear, kind of the bony part, the bald bony part behind your ear. Historically, another one that was common was the clavicle, so actually sort of going down inside the shirt and sticking an electrode on your collarbone there. And again, the reason for doing that was this thinking that it's far away from the brain, so it's going to be a more neutral reference location. The problem with that logic is that the body is conductive, right? So with an appropriate configuration of electrodes, you could record EEG from your big toe. Wouldn't be very good, it wouldn't be very strong, but you could do it because your brain activity does conduct through your whole body. So you're never going to find a location on the body that's not capable of recording or detecting EEG or brain activity. So there's really no point in going to the nose, which is kind of distracting and weird, and you're like cross-eyed looking at this electrode on the tip of your nose, or like reaching into somebody's shirt, which can be super awkward in a research setting or many other settings. Right, so you're dealing with the person's head anyway, you might as well just stick another electrode on the head. And again, because of this differential amplifier configuration that I showed you before, and you think of that formula, so it's, well, I can write it down, right? It's A minus G minus R minus G. And because of that subtraction, you're really isolating the difference between A and R. So even if your reference electrode is on the head, you're measuring the difference between that and this location. And then some other electrode, it's relative to the same reference, and then some other locations. So you're still getting this localized information about each electrode relative to your reference, and it doesn't ultimately matter where that reference is. The one thing that people recommend against is using a reference electrode that's lateralized to one side or the other. Even that, I think, is a bit old school thinking. The principle there is that, well, brain activity, we've got two cerebral hemispheres. Activity tends to be lateralized depending on the task. And so if you have a reference on one side, it could be sort of biased that you'll be more sensitive to like left hemisphere than right hemisphere activity because the left hemisphere is farther away from a right mastoid reference location or something. But if you really start thinking about that, that also means that if you have a reference at the back of the head, then you have a difference between your sensitivity to the front of the head and the back of the head. And we know that the frontal lobes and the occipital lobes do different things. So again, it's pretty arbitrary. So these days, as you see, there's a variety. Like the vertex, so right at the top of the head, is actually a place where the P300 is biggest, the N400 is biggest. Lots of kinds of components, but it still works as a reference location for reasons I'll explain in a minute. In the system you'll be using, the reference electrode and the ground electrode both go kind of up here, so they're like between the vertex of the head, the top of the head, and the nasation, and they're right next to each other. The nice thing about that is that you get a nice subtraction because they're so close together. They're basically measuring the same thing, and so that R minus G difference is quite minimal. What you do find is that when you record, say with that reference ground configuration, your active electrodes close to the reference are going to look pretty flat. Because again, you're taking the difference between the active and the reference, and those electrodes too close together, they're not going to show you much difference because again, the brain activity is very smeared and spread out over things. And so that's where the re-referencing comes in, which is almost the next topic. The other thing you can do, and this is, you can do this during recording or after the fact, is take the average of all the electrodes and subtract that from each individual electrode and effectively use that as the reference. So that's what we call an average reference. And it's based on the principle that every source of brain activity is a dipole. So it's got a positive end and a negative end. And so if your head was a perfect sphere and you didn't have a neck and we were able to put electrodes evenly spaced around that entire sphere of your head, we'd be able to capture sort of the positive and negative ends of every dipole, and they'd cancel out. And so the reference would be, the average of all those would be 0. Because everything should be sort of equally positive and negative at different ends. But again, that's predicated on having electrodes all the way around the head, having evenly spaced electrode coverage, having equal impedance at every electrode. There's a lot of sort of assumptions that aren't quite met. Again, this system with the net was designed to facilitate the average reference. They intentionally put more electrodes down low in kind of like areas on the face where there's no brain activity, right? I mean, it's going to conduct, but you're going to be relatively insensitive to brain activity. But it was based on this principle that if we have better coverage, we can get a better average reference. And for reasons I'll talk about in a minute, there are some advantages to the average reference, but there are some disadvantages as well. Okay. All right, that's one test that passed. I'm getting notifications, and they're not showing up on the screen. Awesome. Okay, so the reference location in some cases, for the sake of recording, the choice of reference location is arbitrary, and it doesn't so much matter. That's only because after the fact, we can re-reference to any other location on the scalp or to the average of all the electrodes. And it's very simple because, again, the referencing is just this subtraction. And so if we want to re-reference to some other location, we basically take the time course from that electrode and subtract it from every other electrode. And then that one will go flat because when you subtract it from itself, it's 0. And you basically now have every other electrode as relative to that reference. And often, like I mentioned, the mastoid, so people use a reference on one mastoid, say the right mastoid during recording, and then afterwards they'll take the average of that plus the left mastoid, and then you don't get this hemispheric bias. In this case, what I've done is taken one set of data that we recorded in a face processing study. So remember last time I talked about the N170, which is a negativity. It tends to be biggest, depending on your reference, but biggest over sort of near the mastoids, behind the ears. It's thought to be generated in the inferior temporal lobe and the fusiform gyrus. And so you get generally a bigger negativity back there, base of the skull, and then a positivity around the top of the skull. So the thinking is if you imagine the dipoles sort of stuck in the temporal lobes, the negative parts are pointing kind of down and outward, and the positive ends of the dipoles are pointing upwards and towards the center of the head, so you get this big positivity in the middle and a negativity on either side. But again, it depends on where you put your reference electrode. So in this case, what you're seeing, the waveform plot here is what we call a butterfly plot. And so up until now, when I've showed you ERPs, I've shown you either a single electrode or sort of multiple electrodes, each plotted as a separate axis. Here, we're just taking the data from all the electrodes, and this is ERP data, so time off to the onset of the phase presentation. Positive is up, by the way. And we've just overlaid all the electrodes traces individually. And so what this does is it sort of helps you identify where in time you get the biggest component peaks, which in this case you get a P1 for faces just after 100 milliseconds, this N170 in about 170 milliseconds, and then an N250, in this case a bit earlier than 250 milliseconds. But you get these three components. And also with the butterfly plot, you can sort of see, because this is every electrode, so depending on where you are, like with this P1, you can see the red areas are the more positive parts of the scalp with this reference, this average reference. So those are the positive bits there. Then there's negativity at other parts, and so you can see the negative part. But in these butterfly plots, you can see that as you change the reference, the relative number of electrodes that show a positive effect or a negative effect is going to differ, right? So once we go to the Bayesian reference, we basically get none of the electrodes showing any sort of negative peak. Vertex reference, same thing. Average mastoid reference, we actually get the opposite for this P1, where we don't really see a positive peak at all, but just negative. And again, this is all just because we're sticking the reference or making the reference electrode at a different location. So if we think the average reference is sort of the most neutral, because we're subtracting the average of all of these electrodes, start from that point. So the positivity in that case is biggest over the sort of back part of the head, the P1. Then the N170, this is kind of the canonical scalp distribution that I showed you before, with the negative peaks kind of behind the ears in each case, and then this positivity in the middle. Another thing I'll point out, when you're looking down at these scalp maps, it's a bit counterintuitive, because if you imagine, and I'll sort of bend over, if you look at the top of my head, the base of my skull here, the mastoids, you can't really see them from the top, right? Because your head is a sphere, or not quite a sphere, but it starts wrapping under. And so when we plot these, it's like you taking my head and sort of squishing it flat, and the lower parts of the head get pushed out to the sides. And so it might sort of look like those negative peaks are more over my parietal lobes or something, but in fact it's showing the lower parts of the temporal area there. All right, so N170 and then the N250, there's not too much going on there. If we take the Bayesian reference, the data look pretty similar. And if you think about the Bayesian, again, is the bridge of your nose. So that's pretty far away, both from the top of your head, where we're seeing this positive peak, and from the backs of your head. So it doesn't seem too surprising that that's going to look a lot like the average reference. The other ones, though, are more different. So the average mastoid reference, the P1 has gone from looking like a big positivity at the back of the head to a big negativity at the front of the head. The N170 now looks like a big negativity at the front of the head, or positivity, and very little in the way of negativity where we typically expect the N170. And the N250 also, now you're seeing more of this positive peak. The reason for that, of course, is that we've now put the references on the mastoid, which is right close to where the N170 typically is. The negative part of the N170 is typically biggest. And so the difference between your reference electrode and where that effect is big is almost nothing. And so you're essentially subtracting out the negative part of the N170 from your data. and zeroing that out. And so you don't get the same magnitude of effect. It's much more positivity there. And then sort of conversely with the vertex reference, so vertex again is the very top of your head. Now P1 maybe looks a little more extensive. It's the N170 here that's really the biggest difference compared to the average reference. Right, so now the negativity is much bigger, but that positivity that we normally see over the top of the head has gone away because, again, that vertex electrode that we chose as our reference is measuring the positivity. So you're basically subtracting that positivity out from that electrode and all the electrodes around it. So you're relatively minimizing that. Now, the good thing is that, again, this is exactly the same data set. I've just mathematically re-referenced to show you the different things. So you can get any one of these patterns out from the same data, just depending on where the reference is. So the more important thing is that you know what you used as a reference electrode, and your choice of reference electrode makes sense in the context of the component you're looking for. So in looking at phase processing, the Bayesian is a very common one in studies of phase processing because everybody knows where the N170 is and the Bayesian's far away from it. The average reference is another one. Whereas these average mastoid or vertex reference are not typically used. And in fact, it was interesting quite some years ago now. There were two groups who were looking at phase processing, and they were actually comparing phase processing with other kinds of visual objects, so like cars and household utensils and houses, I think. And one group was finding fairly consistent differences. So any visual object will give you an N170 type ERP. Even printed words give you an N170. But the relative lateralization, so how big it is on the left or the right, differs. So words tend to be bigger on the left, faces on the right. And comparing faces to other objects, one group was finding that they had distinctive, and this is where having more electrodes was kind of useful, is they had similar scalp distributions with the negativity at the back, but detectably different. So enough that you could do statistical comparison and get results. Another lab was doing similar studies, similar kinds of stimuli, and not finding the effects. And there were back and forth arguments about who was right and the faces processed differently by the brain. And then they realized that the difference in the data was actually because the labs were using different reference electrodes. And once the lab that wasn't finding the face object differences used, I think it was the Bayesian reference, but used whatever the other lab was doing, their data looked more like the data from the other lab. So these things do have real world impacts, and you do have to think about them, and it's important in looking at data when you're reading a paper to also be mindful of what they used as the reference. But again, it's at least it's sort of recoverable if you choose the wrong reference anywhere along the way. That said, it actually has more of an impact when you're doing analysis between conditions, which, as I said last time, is usually what you want to do. Is you don't want to just look at the ERPs for upright faces. You want to compare that to inverted faces, where you're basically subtracting out everything that's common about the faces and isolating that upright inverted aspect of it. And here, I'm not going to go into as much detail, but you can see that when we do the subtractions, especially thinking that, again, people typically will focus their statistical analysis in an N170 study over these inferior temporal electrode regions. So, I showed you that ROI map before. If you were targeting the N170, you probably wouldn't bother even analyzing any of the electrodes over the front of the head. You'd just isolate the ones at the back because that's where the effect is going to be biggest, as long as you chose the right reference. And so you can see here just in terms of the amount of how blue is the area where we're seeing the biggest N170s before versus sort of how white or red it is. That actually differs. And so I'm pointing at one point at the N170. In all cases, you can see there's sort of an effect, and there's like a little circle there, little circle there, and this is typical that faces, again, are a little more right lateralized. But the actual amplitude, like the magnitude of that difference, which is ultimately what's going to go into your stats, is biggest, in this case, with the vertex reference, and smallest with the average mastoid reference.